Building a quantum computer isn't just a physics problem. It's an engineering trade-off that gets harder with every photon. Every team developing a quantum chip eventually faces the same three-way engineering decision. Which photon source should we use? Which detector provides the best performance? And which photonic platform offers the right balance of scalability and manufacturability? Here's why it's hard. Quantum information can't be amplified or regenerated if something goes wrong. Every lost or degraded photon directly reduces the probability of completing a computation. And fixing that, tighter process controls, better packaging, more optical testing, all of it adds cost and cycle time. Quantum design becomes a balancing act between three competing objectives. Fidelity. How accurately can the system generate, manipulate, and detect quantum information? Researchers demonstrated quantum interference between single photons transmitted over 180 miles of optical fiber. For the photons to interfere successfully, their wavelength, timing, and other properties had to be nearly identical. Loss. How many photons survive from source to measurement? Recent demonstrations of deterministic quantum dot photon sources with system efficiencies exceeding 70%, an important milestone because they move beyond the theoretical loss tolerance threshold needed for scalable architectures. Cost. How much testing, integration, and manufacturing complexity can the architecture support? There's this constant balance that has to occur, says Keith Shobe, Vice President of Technology and Strategy at Advantest. We need to apply the budget to get as much test coverage as we can at the best quality for that budget. That's where the challenge is. Unlike classical electronic systems, quantum information cannot simply be amplified or regenerated if errors occur. Every lost or degraded photon directly impacts the probability of completing computations. There are a few approaches that are being taken to create the optimum balance. The path to scalable quantum computing may ultimately depend not only on building better photonic devices, but on building better insight into the data those devices generate throughout the manufacturing process. Contact YieldWorks to see how